Neural networks are computational models inspired by the structure and function of the human brain. These models attempt to mimic how our brains process information through interconnected neurons. Neural networks consist of interconnected nodes, or neurons, organized in layers. These layers include an input layer, one or more hidden layers, and an output layer. Each artificial neuron receives inputs, multiplies them by weights, and processes them through an activation function to produce an output. The connections between neurons have weights that determine the strength of the signal passed between them. Neural networks learn through a training process where data is fed into the network and the weights are adjusted to minimize the difference between the predicted output and the actual output. This learning process allows the network to recognize complex patterns and make predictions based on new inputs. Neural networks can identify patterns that might be too subtle or complex for humans to detect. By mimicking the human brain's structure, neural networks have become powerful tools for solving a wide range of problems in artificial intelligence. Let's break down the structure of neural networks by examining their fundamental building blocks: neurons and layers. The basic building block of a neural network is the artificial neuron. Each neuron receives inputs, multiplies them by corresponding weights, sums them up, and applies an activation function. Weights determine the strength of connections between neurons. Each input gets multiplied by its corresponding weight. A bias term is added to the weighted sum, allowing the neuron to shift its activation threshold. The activation function introduces nonlinearity, enabling the network to learn complex patterns and relationships. Activation functions are crucial as they introduce nonlinearity into the model. Popular activation functions include ReLU, sigmoid, and tan. Neural networks are organized into layers. A typical network consists of an input layer, one or more hidden layers, and an output layer. The input layer receives the initial data, such as pixels of an image or features of a dataset. Hidden layers perform the actual computations. Each neuron in these layers processes information from the previous layer. The output layer produces the final result, whether it's a classification, prediction, or any other form of output. The arrangement and number of these layers define the network's architecture. The connections between neurons are represented by weights, which are typically initialized randomly and adjusted during training. The power of neural networks comes from this layered structure. By stacking multiple layers of neurons, the network can learn increasingly complex representations of the input data. Neural networks learn through a process called training, which involves backpropagation to gradually improve accuracy. The training process begins by feeding data into the network. The network makes predictions which are compared with the actual expected outputs. Next, we calculate the error or loss, which measures how far off our predictions are. Then weights and biases are updated to reduce this error. This process repeats many times, with the network gradually improving its accuracy until it converges to a solution. Backpropagation is the key algorithm used to train neural networks. It starts by calculating the error at the output layer. Then it propagates this error backward through the network, layer by layer, calculating how much each connection contributed to the error. Finally, weights are adjusted using a technique called gradient descent, which helps minimize the error. Gradient descent works by minimizing a cost function, which represents the error of the network across all training examples. The optimization process can sometimes get stuck in local minima, which are suboptimal solutions. The ultimate goal is to reach the global minimum, representing the best possible model. The training process is iterative, with the network learning over multiple epochs. Each epoch represents a complete pass through the training data. As training progresses, the error typically decreases rapidly at first, then more gradually as the network fine-tunes its weights. To summarize, neural networks learn by minimizing the error between their predictions and the target outputs. Backpropagation calculates how each weight contributes to the error, and gradient descent adjusts these weights to minimize the overall error. This training process is iterative, and typically requires many epochs to converge to an optimal solution. Neural networks are revolutionizing numerous fields with their ability to learn patterns and make intelligent decisions. In natural language processing, neural networks power language translation systems, converting text between languages while preserving meaning and context. Neural networks also power speech recognition systems and conversational AI like chatbots and virtual assistants. In transportation, neural networks enable self-driving vehicles to perceive their environment, identify obstacles, and navigate safely. In healthcare, neural networks assist in medical diagnosis by analyzing patient data, medical images, and identifying patterns that might indicate disease. In finance, neural networks play a crucial role in fraud detection by analyzing complex transaction patterns and identifying suspicious activities. Neural networks are now affecting billions of users every day, powering applications from social media and search engines to smart devices and research tools. Graph neural networks, or GNNs, are experiencing what researchers call their ImageNet moment, rapidly gaining importance in the field of deep learning. Unlike standard neural networks, GNNs are specifically designed to work with data that has a graph structure, where relationships between entities are critical. Graphs can take many forms, such as multigraphs with multiple types of relationships, or hierarchical graphs with different levels of organization. But how do graph neural networks actually work? At their core, GNNs learn by aggregating information from neighboring nodes in the graph. In this process, each node collects information from its neighbors, updates its own representation, and passes this updated information to the next layer. This allows the network to capture both local and global graph structure. Graph neural networks can perform a variety of important tasks. These include node classification, link prediction, graph classification, community detection, graph embedding, and graph generation. Node classification, predict properties of nodes. Link prediction, determine if nodes should be connected. Graph classification, categorize entire graph structures. Community detection, identify clusters within graphs. Graph embedding, map graphs to vector representations. Graph generation, create new graph structures. GNNs are finding applications in numerous domains. In drug discovery, they predict molecular properties and interactions, helping researchers identify promising compounds. In recommendation systems, GNNs model the complex interactions between users and items, enabling more personalized suggestions. Social network analysis is another key application, where GNNs help identify communities, influential users, and patterns of information spread. As graph neural networks continue to evolve, they're pushing the boundaries of what's possible in AI research, enabling us to solve increasingly complex problems involving relational data. Neural networks continue to evolve rapidly, with research focusing on several key trends. Current AI research is advancing in several directions, with innovations in deep learning, reinforcement learning, and unsupervised learning. These innovations are pushing the boundaries of what neural networks can achieve, making them more capable and versatile. A major focus in current research is creating more efficient neural network models that require less data and computational power. These advancements enable training larger models with fewer resources, as shown in these performance comparisons for large language models. Hybrid models, which integrate different neural network architectures, are becoming increasingly common. These models combine the strengths of different architectures, such as CNNs for image recognition and RNNs for sequential data processing. Reinforcement learning is a powerful approach that allows AI systems to learn through trial and error interactions with an environment. This technology is becoming increasingly prevalent in various industries, including healthcare for treatment optimization, finance for trading strategies, transportation for traffic management, and robotics for task learning. Unsupervised learning is another area seeing significant advancements, where algorithms find patterns in data without explicit labels. This approach offers several benefits, including discovering hidden patterns in data, working with unlabeled data sets, reducing the need for human supervision, and scaling efficiently to massive amounts of information. These emerging trends in neural networks promise to make AI systems more powerful, efficient, and applicable across a wide range of industries.